Okay. So we're arranging this, solving for, and I usually keep them as inverses because I'm wimpy like that. Even though I want A, I'm going to keep it as the inverse of A. And then one of my last steps is going to be to flip it. Okay. So in this case, all I need to do is plug in the K we were given, the time of interest, and the initial concentration. And it never hurts. I like the variable A. It's nice and clean, but you see in red what I've done is associate. Anytime you see A working this problem, that is your butadiene. That is your butadiene, or this. That's your C4H6. So here we go. The inverse of the molar concentration of A is equal to KT. So our K is 144 liters per mole per hour. Our time of interest is 1.00 hours. So of course the cool thing there's a lot of cool things there. But our units of hours cancel. We're left with units of liters per mole. Plus the inverse of the initial molar concentration of A. Inverse of the initial molar concentration of A. 1 over 0.0200 moles per liter. Now again, we got that funky units of moles per liter in the denominator, which means liters per mole. So by my count, we have liters per mole and liters per mole there. Okay. One's pretty easy, right? Now, however you want to do this, I can't remember how my notes do this. Oh. Well, when you go ahead and tap this out on your calculator, you will get the inverse of the molar concentration of A at that time of interest is equal to 194, that's liters per mole. Now, how are we going to get it in moles per liter? What do you think? How am I going to go ahead and fix this? Right, exactly. Exactly. Divide 1 by 194. And that 194 is units of liters per mole. Exactly. And so that will give you units of moles per liter. So 1 divided by 194 gives you a value, 3 sig figs, of 0.00515, and units would be moles per liter. Any questions about that? Okay. Well, let's work the second one. We don't have a second equation to use okay. But in this case, we were given the molar concentration of interest and asked to find time. So we basically want to get time by itself, so we can rearrange this, and it looks like this. Time by itself is equal to quantity, right? Time by itself is equal to 1 over K times the quantity, the inverse of A minus the inverse of A0. I think for a problem like this, it's easier to rearrange your equation first, your time concentration equation first, and solve for your variable. So this is our little box of what we know. A few slides ago, introduced that the concentration of interest is 0.0020 moles per liter. So plugging in then, it looks like this, where the time is equal to the inverse of K, so time is equal to 1 over 144 liters per mole per hour. Isn't that crazy? So those units, these units are going to actually be what? Hours, moles, hours per liter. Then over here we have the we have the molar concentration of interest. So that's our A, and this right here is the inverse of our A0. All right. Now, if you're like me and if you haven't done these problems very, very often or whatever, you need to make sure you make sure you're doing it right. So, rounding it to two significant figures, I got 3.1 hours. Oh, excuse me.
So all those liters per mole cancel out.
Right, exactly.
Oh, yeah.
Yeah. Yeah, this, I said it'd be hours per mole liters, and then these actually would be liters per mole. Yep. All right. It's a beautiful thing. All right. Now, one thing I need to talk about is this special sweet time, and they call it a half-life. All half-life is basically you started out with this amount. The time it takes to get half of that initial amount is your half-life. That's it. That's it. And so let's go ahead and we can describe that is T1 half is when your concentration of interest is 1/2 of the initial concentration. Does that make sense? Okay. So let's kind of do a proof and consider what half-lives are like for first order and second order reaction kinetics. So if we look at the first order first, so where there's the T, I'm going to substitute T1 half, and where there is the A, I'm going to substitute 1/2 A0. It looks like this. Okay, and then that new equation will be the half-life equation. Well, it starts to look like this. This is like a proof. So we basically have the natural log now of the quantity 1/2 A0 over A0, so my A0s are going to cancel, right, is equal to negative K T1 half. So it looks like this. So the natural log of 1/2 is equal to negative K T1 half, half-life. So this is just for first order. We just did the proof for first order kinetics. So rearranging that, dividing both sides by negative KT, the half-life, T1 half, is equal to 1 over negative K times the natural log of 1/2. That also, I think, will be on your sheet. Or will it be this one? The natural log of 1 over 2, oh, I know, this is, okay, so what I've done between these two is, how do I say this? The natural log of 1 over 2 is equal to negative ln of 2, okay? Then if I do that, I can actually take these negatives and they cancel out, so I get the natural log of 2 over K. It's legit, trust me. And so do I have a calculator here? So the natural log of 2 is a number. Sometimes instead of seeing it that way, you'll actually see it. We got time. There's my natural log key. There's my ln of 2. Oops. So the natural log of 2 is a value of 0.693. So I've seen it that way too before. So the point here is that your half-life does not depend upon your initial molar concentration of A. It does not depend upon that, because that doesn't show up in our half-life equation. So that's a half-life equation for first order. So this actually is looking at reaction where it is first order. So if it started out as 100, in this case we're looking at the partial pressure, 100 millimeters of mercury. When it had decreased from 800 to 400 millimeters of mercury, that segment of time you see along the bottom there, that's its first half-life. Yes?
So as long as we know the rate constant, we can find the half-life.
Yes.
Okay.
And it's first order.
Right.
Yeah. Yep.
Or if we know the half-life, we can find the rate constant.
Right. Yes. Hey, that's a very good point. In fact, I'm going to put this over here. I'm going to add this to our pile right here. You are totally with it. So half-life for first order is equal to ln of 2 over k. Yep. And so what Mike was saying is, if you know k, you can get half-life. If you know half-life, you can get k. Exactly, for first order. Yep. So this is kind of neat, I think. It kind of has this sort of multiple half-lives. The first half-life, in this case, is to go from 800 to 400. Okay? The second half-life, guess what? Is to go from 400 to 200. Okay? The next half-life to go from 200 to 100. What's the relationship of those half-lives? They're halved. How would you, so those are time segments. How would you compare those 3 time segments?
Just divided by 2.
Not divided by 2. How would you compare this time, first half-life, versus this time, versus this time?
Oh, yeah, I was looking at the other thing.
What do you think? They're equal. Yeah. And that's just a cool thing about first order reaction kinetics. So it takes the same amount of time to use up half of what you got in a certain time. I think that is so cool. It's mind-boggling to me. Okay? Anyway. Okay, so let's change it up. Let's go ahead and do the substitutions we did before, but let's look at second order reaction kinetics. So the substitutions we did before look like this. Okay? So we know that that's the integrated time concentration equation at the top there. And we need to substitute our, instead of our A, we're going to put 1/2 A0. Instead of our time, it's going to be T1/2. Because it's the half-life. It's a special time. So it looks like this. And if you're like me, you're like, how does that work? So we need to take that 1/2 in the bottom and fix it. So it looks like this. So we have 2 over A0 minus 1 over A0 is equal to K T1/2. Well, that's not too bad, that math thing. The 2 minus the 1 gives me, what, 1. So it becomes 1 over A0 is equal to K T1/2. And to get T1/2 by itself then, T1/2 is equal to 1 over K, and then also times 1 over A0. So that's this one here. Now this one's not as helpful, okay? This one, and I guess I go back to kind of what you said, Mike, this one you could find, you know, half-life or K if you also had the initial concentration. Okay, so half-life does depend upon K and the initial concentration. They're both in the denominator there. Okay, so here's several tips in working these problems. So my big thing is you have to know before you work one of these problems, get your wits about you. Is it first order? Is it second order? Is it zero order? which we didn't talk much about that. The other one is if you don't know which order it is, if you look at the units of K, that will tell you or give you some good information. Now remember, K actually has to compensate for the overall reaction order, okay? But in some of the examples we've been working, we only have one reactant. So the units of K actually are tell you directly what the reaction order of that one reactant is. And then the other one for the third one up there, if K isn't given, you can sometimes get K, and you need K, you can get it from your half-life directly if it's first order. And if you know the initial concentration, okay, you can get it for a second order too. That last one up there, let's see, how do I say? Sometimes I try to give an example of this one. Okay. So if we look at its first order, sometimes you only want to know, like for instance, you want to know when you have the molar concentration of A is, let's put 50% of A0. Okay, so there are times when you aren't given what the exact molar concentration of A is for question time. You're just giving, you want it to be half gone. So my point here is if you want it to be half gone, do you see where you can use this equation and you can actually simply put, what would the ratio of A to A0 be if we want it half gone? What's in decimal form?
1, 2.
Yep, 1 over 2. Yep, and 1 over 2 is 0.5. Exactly. We could just plug 0.5 in there. Yep. The other thing, don't let this throw you off. I'll try not to let it throw me off. Is that this actually is the amount remaining. It's not the amount that's reacted. And there's definitely a difference there. So, for instance, if you want the time at which, let's see, 75% of A has reacted. Let's think through this. 75% of A has reacted. How much of A is remaining?
25.
25%. What would we put right there? 1/4, yep. Or 0.25 would go right there as the ratio remaining. Okay, so that's an important one. All right. So let's take a quick look at these problems, and we'll go back to the other problems. Yeah, there's one of these problems that you aren't going to do. So let's see which one it is. Or wait a minute, no, that's in the previous set. There's one, I think you're doing all these. 14, 17. Wait for it. There we go. All right. So A goes to form products. What percentage of, oh, and it gives you the half-life. Oh, first order. I was like, well, it didn't say what order it was. So it's first order, so we're dealing with all this stuff over here. What percent of a sample remains unreacted after 9 seconds? Let's see what my hints are here. So I just went ahead and jotted down everything we know about first order. All right. This is a classic example where we're not given K, but you're given T 1/2, and you can solve for K. Okay? So because you're going to need K in order to use the integrated time concentration equations. You can get K from the half-life. So this actually kind of goes back to what I was trying to say a minute ago. What the percent means is the relative amount of A remaining times 100%, or times 100. So if we use this top equation, we basically are solving for the ratio of A to A0. So we plug in the K that we get from our half-life. We plug in the time of interest, which was 900 seconds. And then do I give another hint? Yep. And then to get to the ratio, because basically you're going to have ln of A over A0 is equal to some number, which you totally got. Then to get to that ratio, you need to take, how do I say this? You need to take this, the e raised to the negative kt, to get to your ratio. Is that all my hints? Yeah, that was all my hints for that. In other words, for that last bit down there, okay, if I'm after that ratio right there, I can take e raised to the ln of A over A0 is equal to e raised to the negative kt. Are we good with that? Okay, good. So if we're good with that, since these are the same bases, actually this is a wonderful thing because it boils down simply to the molar concentration of A over A0 is equal to e raised to the negative kt. Okay? So,
Since they have the same bases, it would be A over A0 is just equal to negative KT.
no, because you didn't do anything fancy over here. You still have e raised to the negative kt. You had no way to, you're stuck with that. But what you've done is to basically get to this ratio. Okay. For B, it says, what is the reaction rate when your molar concentration is 0.50? Oh, yeah. So this goes to the rate law expression. So up here, that's right. Okay, remember the rate law expression says, what is your rate given your K and molar concentration? So we go ahead and set the molar concentration is at 0.50. You guys got K from your half-life, so that one's not too bad. The next one looks like this. First order, again, it gives you the initial. I went ahead and put that 0 up there, initial. And after 54 minutes, it gives you the concentration. Okay, so it's first order. That's all you know about first order. Sometimes I think I'm just stalling when I write that down. Oh, I was like, how did I do this? So in this one, actually, you were given kind of a snapshot of the molar concentration of A after 54 seconds. You can plug that in there to knock out the K. Isn't that cool? I think so. I look surprised, but all right. And you're after what time will your molar concentration be when A is equal to 0.025? You're going to go ahead and use the first equation to make that work, kind of like we did is our example. What is the rate of the reaction when your molar concentration is 0.025? You're going to use your rate law expression. Okay? Again, first order. What is first order? I'm getting impatient. All right. I'm just going to kind of bump it up against the clock, so I'm just going to kind of push those out there. This one looks like this. Finally, show its first order. You're going to have to plot it. What is K? Get that from the slope. I think you're going to have to plot this one.
So for these homeworks, do you want us to turn in our Logger Pro for these problems?
Yep, turn in Logger Pro. What I've seen sometimes students, like, yeah, you have to turn them in. Or take a snapshot or something. I mean, prove to me that you use Logger Pro. Be creative if you think you can do that. So I just put all these out here. Yeah, there's a lot. I was kind of talking before everybody got here that Monday, this is good to get through these both parts, because Monday we're actually talking about one last topic, and it's the kind of what we call reaction kinetics. It's kind of like the steps behind the scenes why a reaction occurs. Okay, so mechanisms, I guess it's called mechanisms. Okay, all right. So
are we doing the problems though for the other part?
yep, you want to take a look at those right quick? There's actually one in there. So remind me what they'll start with. 14 what?
27.
Yeah.
You had to bring it up.
So you guys knew they'd be due, you sillies. Okay, so for this one, again, you need Logger Pro. You can see the Roman numeral 1, 2, and 3, the time concentration data run at 3 trials. One of them is going to be 0, one's going to be first, one's going to be second order. Okay, so you need to go ahead and knock those out on Logger Pro. It's going to be a Logger Pro sort of weekend. But this is the last weekend before your test. So, let's see. Oh, yeah. The one that I said don't worry about is number 29. It deals with half-life, and we hadn't dealt with half-life in part this one, but you should be able to do it now, but don't worry about it.
Do it or not?
Don't do it. Do it for extra credit.
Get some extra credit on
No
it?
one ever does my extra credit when I throw it out there.
Hey, I get extra credit.
Do it for extra credit and put a little star next to it.
The whole assignment?
Sometimes, no, because then you'll just do that one. You won't do the rest of the assignment. Only valid if you do the others.
So if you do everything else and that one, then you get 20 points.
Right,
But if you just do that one, then that.
right. Because I'm catching on. So I'll push these out there.
Did somebody do that, just the extra credit one last time?
I think so. I lose track,
I
but.
didn't do any of them.
So I'll be checking my email off and on if it works. So feel free to drop me a line or text. Tell me how your weekend's going.